seems like they know right when it's time that I need to leave class, that then everybody calls. All right, so we'll start from the current slide. Okay, yeah, Screencast-O-Matic started. Before we get started on this, I did want to do the announcements, though, and I wanted to get them on Screencast-O-Matic. Now, this first one is an awfully short deadline, okay? I think I announced this last Wednesday, but if not, if you missed it or if I forgot to, sorry about that. But you received emails on several of these, and these first two for sure, that there are some scholarships, presidential scholarships from First UAB, also University of Alabama, Tuscaloosa. Now, you must be graduating this term. Or any of you graduating this term, completing everything this term and graduating? No. Okay. Well, then don't worry about that. If you know of anyone who's graduating this term, they have to get at least the first part of this in by end of business today, 5 p.m. today, and the rest of it has to be in by March 1st, which is Thursday. Okay? So that's that. Math team still meeting, as far as I know, on Fridays at 12 noon, and today, Mondays, at 3 o'clock, over in C100 in the Science Building, Birmingham West Campus. However, this Friday you will not be meeting, I don't think, because Mr. Geraci is going to be at a meeting in Jasper, but she'll probably let you know that today. Okay? So, but they are meeting today as far as you know, right? And today is also the last day of our homecoming week. Game dates is tonight. Homecoming parade starts at 4 o'clock this afternoon on the Birmingham East Campus. I think it's by the A.G. Gaston building, the gazebo there. And then the homecoming parade will go across, down Wilson Road, and into the Birmingham West Campus and stop at the gym. And that's the Arthur Shores Fine Arts Building, which is also the gymnasium, on the Birmingham West Campus. Then this evening, the Lawson State will be hosting Gadsden State. That will be our homecoming game. The women play at 5:30 and the men at 7:30. That's on the Arthur Shores Fine Arts Building, which is also the gymnasium on the Birmingham West Campus. Okay, so that's this afternoon and evening. I think I announced to you before the tutoring schedules. Not that many of you probably need tutoring, but you can get it if you wanted it. But even better, or more so, you are probably quite well qualified to tutor. So if you are interested, contact either Student Support Services just down the hall here. I found out last week Miss Hollins is no longer here, so you go on around to Miss Harris, LaShondra Harris, and her name was listed, but I thought, wow, Miss Hollins is the coordinator, but she's no longer with us, so it's Miss Harris is the one who's taking over that for now. Okay? Now, a couple of other things that are coming up. Wednesday of this week, the 28th, we have a meeting from 2 to 4 over in the Ethel Hall building. However, I've got a class that's 2 until 3:15, so I won't be able to be at the meeting until closer to, shortly after 3:15. So I won't be available from 2 to 3:15 because of my class, and then after 3:15 until 4 o'clock because I'll be in the meeting. Okay? Let me mark. Remind me? Tyler. Okay. Tyler Fredericks, right? Okay. Now, if that wasn't enough, on Thursday, March the 1st, I have another meeting, and this is from 2 until 5, boo hiss, and this will also be on the Bessemer campus in the President's Conference Room over in the Ethel Hall building. So Thursday from 2 to 5, in fact, after 2 o'clock on Thursday, I'll probably not be available at all because the meeting will go till 5, and generally I'm off campus by 5:15. So if you catch me between 5 and 5:15, and actually the meeting may actually end a little early, but you know I can drink kind of. Okay, so I might be back in the office a little before that. Okay, and then finally, none of you are graduating. Is that correct? Are you graduating this term? You are graduating this term. Okay, finishing everything this term. Okay, now there are a couple of scholarship opportunities out there. One from UAB and one from the University of Alabama, Tuscaloosa. Presidential scholarships. Something has to be turned in by 5 o'clock today. Check your email. You got this in the email. This was back Tuesday of last week, the 20th. You got both of these emails. One was 6:39 in the morning. The other was 6:40 in the morning. Some administrator needs a lot. No, I'm sorry, I didn't say that. But anyway, they sent these out then. So there's something that's due by 5 p.m. today. The rest of it's due by March 1st, if you're interested in either of those scholarship opportunities. And then what I was just about to announce is there are meetings next Monday, Tuesday, and Wednesday for graduation. Monday's meetings on the Birmingham campus, ACAP building, first floor theater, but that's in the evening, 6 p.m. Tuesday's meeting is here on this campus, right across the parking lot here in the Ethel Hall building, Ethel Hall Auditorium. Now, if you're going to this one, walk up around the side of the building. Don't go in through the parking lot level. You can, but if you have to find your way up the stairs and that kind of stuff. But if you walk around the building and come in the entrance that way, when you go through those glass doors, the auditorium is immediately on your left when you walk in. And then Wednesday's meeting on the 7th, next week, that will be at 1:30 on the Birmingham West Campus, ACAP building, first floor theater. Okay, so that's coming up. Got all of you marked here. Believe that we are beginning with example 9, and they don't have example 9 in the slide set, so it'll say example 8, but we will go from example 9. Now, before we get into that, any questions on anything we've covered so far? Any? None? All right. Now, says differentiate both forms of this equation. Okay? Y is equal to, first they give it as 1 minus cosine x over sine x. Okay? Now, stopping there, how's a different way you can express this? Okay? Here we have a difference in the numerator, a common denominator. So you could actually split this into two different fractional forms. And what would they be?
One over
sine x minus
1 over
cosine x over sine x. Okay? Now, while we've got that on the board, what is 1 over sine x? Cosecant x minus what's cosine over sine x? Cosine x over sine x.
tangent.
Not tangent.
Cotangent.
Cotangent. Okay. So, what they said is differentiate both of these forms. Let's differentiate this form, and then we'll differentiate that form and see if we get the same answer. We sure better, haven't we? All right, so let's do the first one. What are you going to need to differentiate that y? In other words, y prime would then be, and what rule would you need to use here? Long line means to do what?
Divide.
Divide, and what's the result of a division problem?
Quotient.
A quotient. So what rule would we use?
Quotient.
Quotient rule. And how does that quotient rule go? What's the little sing-songy way?
Low D.
Low D high. So low is sine x times D high. And what's the derivative of the numerator? Derivative of 1 is?
1. No, it's a 0.
0, exactly. And what's the derivative of minus cosine x?
Sine.
Sine x, okay. Okay. Over. Oh, wait, yeah. All we did was low D high. Then we have to do minus high D low, which would be 1 minus cosine x.
Sine x. I mean, not sine x. Cosine.
Cosine x. Okay. And that's over
Sine x squared.
sine x squared. Low. Okay. Sine squared x. All right. Now, let's figure out what in the world that is. Sine x times sine x is?
Sine x squared.
Sine squared x minus, okay, first we have a 1 times cosine x will be cosine x, and then we have a minus times a minus cosine x times cosine x. Minus times minus makes plus cosine squared x, right? Over sine squared x. Okay? Now, anyone want to hazard a guess what sine squared x plus cosine squared x is? 1. Okay. So we have 1 minus cosine x over sine squared x, which is a perfectly legitimate answer, but you could also break that into two different fractional forms, and what would that be? 1 over sine squared x, cosine x over sine squared x. Okay? And what is 1 over sine squared x? Cosecant squared x minus. Now this will take a little more work. What that is cosine x over sine x, right, times 1 over sine x, right? What's cosine x over sine x? Cotangent x times, and 1 over sine x is cosecant x. All right. Now, somehow to me it almost feels like I've got a sign wrong somewhere, but I don't see it. Yes, I think we're okay. Okay. Let's proceed with this. So, if this is also y, what is that y prime? What is the derivative of cosecant x? If you got your book, it's just the previous page. Right in the middle of the page there, right? Yeah, that page right there.
Negative cosecant x times cotangent.
That's it. Okay. And then what is the derivative of minus cotangent x?
Cosecant squared x.
Yep. And that would be a plus. Cosecant squared x. Okay. Now let's look at what we got before. When we rewrote this, this was a perfectly good answer in terms of sine and cosine. In fact, that's how I would have left it. But we also see that turns out to be cosecant squared x minus cotangent x cosecant x. The order of those doesn't really matter, but the signs do, and sure enough, it comes.
Where did the second cosecant down there come from?
Where did what?
Is that because sine x is squared in the?
Okay. All right. You mean this right here?
No, sir. I was talking about the one.
Oh, here?
Yes, sir.
Okay, that's a cosecant. If that's what your problem is, let me first mark.
Now, where did that second one come from on the right?
Okay, wait. Let me get. Right? Is that right? Yeah. Okay. All right.
Is it because sine squared x?
Okay. Where? Here or down here?
Down there.
Down here. Okay. All right. We got this as our result from here, right? Okay with that. Then we said this is 1 over sine squared x minus cosine x over sine x. Sine squared x, right? Okay. And then we took this up here and split that into cosine x over sine x times 1 over sine x.
Oh, that's what I...
Yeah, I'm sorry. I knew I was encroaching on the space there. I thought I was going to need it, so I sort of wiggled around some. Okay. And then, what did I do? Okay. Oh, yeah. We did. This part was cosecant squared x, and this part done like this was cotangent x times cosecant x. Yeah, and then we got the same thing. All right. See that? Make sense? Any questions? I know you just came in, so yeah, okay. All right. And sure enough, we got the same as they did. All right, using the Pythagorean identity, the sine squared x, because sine squared x is 1. Good. Now, the next slide after they go through example 8, this is just stuff we did last time. The summary below shows that much of the work in obtaining a simplified form of derivative occurs after differentiating. Sometimes the differentiation is the easy part, but then getting it into a standardized form, that takes a little more work. Now, the two characteristics of a simplified form are the absence of negative exponents, if you can avoid them, and combining of like terms. Okay. Now, by the way, a little time out here. I guess over the weekend I contracted it, but last night or this morning I woke up sort of a head cold, feels like it's coming on. So if and when that happens, and you may actually hear it in my voice, the way I sound, sorry if I have to run down the hall and clear my head or whatever. So far, knock on wood, I'm feeling okay. But kind of the downside to this is the treatment that I'm taking has basically almost wiped out my immune system. So this, hey, here for trig class, all right. I mean, for calculus class, good. Okay.
I was going to get to you. I'm not going to be here whenever class starts. I have to leave.
Okay.
Those were my tests.
Okay, great. Thank you. Okay. So that's a little scary because this could progress really quickly to something else. I'm hoping it won't, but my immune system is pretty much shot right now. But I think it's getting better. The last blood work that I had was greatly improved over the previous one. But it's still, red blood cells are low, hemoglobin's low, hematocrits are low, but worse than that, neutrophils, which are your fighters, low, very low. Platelets are also low, but they came up. That shouldn't be an issue. I hope not anyway. Unless I happen to have a bloody nose, and then I could have a hard time stopping that. So hopefully that won't happen. Okay, so here's the first. Here's f prime after differentiating. Now, they didn't tell you what f was, but I can almost guess no, I can't. Okay, what it was, but if this is what you had after differentiating, this is probably was your, yeah, I can guess, yeah. The thing that f was there was the first factor in f, there was the first factor in f, and that was the second factor in f. So this is the result of a product rule, okay? Because if this was your first factor, its derivative is 3 minus 4x, and there that shows up here. And if this was your second factor, the derivative of this is 4. So that's where that was. Okay, so this is the result of your differentiation. Okay? We usually don't leave it in a form that's sort of wacko like this. What we do is then distribute here, or multiply here. So this gives you 12x minus, you continue, 8x squared. This gives you 15 minus 20x plus 12x, so that would be minus 8x, right? And over here we had a plus 12x, so that's going to give you a plus 4x. So that's where that came from. And then here we had a minus 16x squared. Here we had a minus 8x squared. That gave you minus 24x squared. And then that was your 15. So, actually doing the differentiation, yeah, it was a product rule, but it wasn't that bad. But then more work is involved to get it into a nice, useful form. Okay? So, what's this? Here's example. Oh, okay. I guess these are the examples we already did. Let's go back and see. Yeah, example one was, yeah, that one. And it took a little while to get it into some sort of nice form, okay? Example 3, they skipped 2, but example 3 was a cosine function, a trig function. And again, it probably was, let's see, make sure, yeah, I think it was a product rule. But you had all this mess. Then you have minus, this becomes minus 2x sine x plus 2 cosine x. Then a minus 2 cosine x, that adds to 0, so that gives you, so again, like I said, combining like terms, you know, that resulted there. This, pretty sure, is a quotient function. This would be in your low d high minus high d low over low, okay? So you get that worked out, then you have to figure out this will be a 5x squared minus 10x squared, so it's going to be a minus 5x squared. And then you're going to have a minus plus 4x, so therefore that comes from, and a plus 5, okay, all over this. So yeah, it's the simplification and you know, part of it almost takes more time than differentiation. Maybe not quite as much, but pretty close. Looks like another quotient rule. Low, yeah, d high minus high d low. That is the derivative of that. Over low. Well, when you multiply this out, you have 3x squared minus 6x squared. That's a minus 3x squared. Here we have a 15x minus 15x, so that adds to 0. Then you have a plus 2x, so there's your plus 2x, and then you have a minus 5, which is plus 5. Sure enough, that works over x squared plus 5x. So you see, it's just manipulating, okay, take your time doing this. I'm doing it pretty quickly. Take as many steps as you need to make sure you don't make a dumb error. Okay? So carry it out as much or as little, as slowly, as rapidly as you are confident in doing. Here was example 9 that we just finished. We had sine x times sine x is sine squared x minus cosine x plus cosine squared x. The cosine squared x plus sine squared x becomes 1 plus 1 minus cosine x over sine squared x. So sure enough, that's it. I don't know why they went back and did this. We had done it all in the steps we did before, but I guess he's just pointing out try to avoid negative exponents, which we weren't using them anyway, and combining like terms, which we always do. So I guess that was worth a slide. All right, let's move on to higher order derivatives. Okay? Just as you can obtain a velocity function by differentiating a position function, you remember that, right? You can also obtain an acceleration function by differentiating a velocity function, because velocity is the time rate of change of position, acceleration is the time rate of change of velocity. Okay? Another way of looking at this is you can obtain an acceleration function by differentiating the position function twice. You start with the s of t, your v of t is s prime of t, the first derivative of s prime. Well, then your acceleration function is the derivative of the velocity function, which then is the second derivative of your position function. Okay? That's your acceleration function. Now, we haven't done that yet, but there's no new mystery to it. You just take a derivative of the previous function, and see what you get. Okay? Okay? That function a of t that we just had is called the second derivative of your position function s of t, and is denoted by s double prime of t. S prime was one derivative, s double prime is the second derivative. Second derivative is an example of a higher order derivative. You can define derivatives at any position of any positive integer order. You can define derivatives of any positive integer order, meaning first derivative, second derivative, third derivative. Positive integers, that's what we mean. For instance, the third derivative is the derivative of the second derivative. Okay, you just keep taking the derivative of whatever you had before. Okay. Now, a little bit on notation. Yeah, they're going to do that next. I was going to do it myself because I thought that's not the only way you can denote it, is s double prime. Okay, here's other ways to denote it. The first derivative is often called y prime, or f prime of x. It's also called dy dx, or d by dx, we had it d by dx of f of x, or that other notation we really haven't used much yet, but the derivative with respect to x of y. Okay? That's saying almost this here. It's just saying capital D is the derivative operator with respect to x, that's your sub x, of the function y. Okay? So your second derivative at y double prime, or f double prime, that makes sense. Now, here's the part that you might wonder why they do it this way. What you're doing, you're taking a derivative of, and a derivative is d by dx. There's our d by dx, okay? It's d by dx of this thing. So d by dx of this, that has your two d's together, so they shorten that and make it d squared y, but you had dx dx, so they make that dx squared. Now, what that means is not d of x squared. That doesn't make any sense. dx is your operator here, and you have that called it d dx dx, that makes it dx squared, and this is d dy, which is d2y. Okay? It's just how they write it. Or d by dx of d by dx of f of x. Okay? So that'd be two d's, d squared by dx squared of f of x. It's basically the same here, except you, instead of y, you put f of x. Put it in y. Or, using your derivative operator notation, you're taking d by dx twice of that function y. Okay? Which is the same thing as this or that. Okay? Triple derivative, third derivative. Okay? Y triple prime, f triple prime of x, d3y of dx cubed, d3y of d by d, ooh, that's hard to say, d cubed of dx cubed of f of x, or capital D, the derivative operator of x cubed of the function y. Now, past 3 primes, we don't keep putting primes there. It gets so hard to count them, because they're little to begin with. So after that, we put 4 in parentheses. Okay? Y in parentheses. If you didn't have parentheses, you think that was y to the 4th power. Not. Okay? In parentheses, that means derivative. The 4th derivative of y, or 4th derivative of f, in parentheses, that superscript 4 means derivative of x, which is d4y dx 4th, or d4 by dx4 of f of x, or d sub x 4th of the function y. And you can keep on going from there on, and the nth derivative, that would be in parentheses in, y superscript in parentheses, that's 4th derivative of y, is 4th derivative of f of x, which is not 4th, nth derivative of y, which is the nth derivative of f of x, which is the dny over dx to the n, or dny over dx to the n of f of x, or d sub x to the n of y. So, lots of ways to write a derivative. Just for general purposes, these are kind of more like what Newton did. Maybe not exactly the same, but similar. This is usually called Leibniz notation, when you have the d-bys, okay? And this is a more recent, that's an operator notation, the differential derivative operator. Okay, pretty much nomenclature, okay? So here's example 10. It's actually a fairly applied problem here. Because the moon has no atmosphere, a falling object on the moon encounters absolutely no air resistance, or so very little you can't even notice. In 1971, astronaut David Scott demonstrated this, that a feather and a hammer fall at the same rate on the moon. Now we know pretty much that if I held a hammer here and a feather here and dropped them here on Earth, the feather's going to, which was the feather here, goes, hammer, right there. Okay. But that's because of air resistance. The feather has a large surface area, very lightweight, and it sort of wanders on down. Okay? But on the moon, there is no air resistance. And this is hard to imagine, but it is true. He held the feather and a hammer on the surface of the moon, dropped them simultaneously. They both hit at the same time. Okay? The position function for each of those falling objects was s of t, that's your position at time t, is minus 0.81 t squared plus 2. Now, what do you reckon that meant? If you go back to our position function before, the height in meters, if you go back to it before, you'll remember it was a minus 4.9 t squared. Remember how we got the 4.9?
Was that the guy on the diving board?
It's what?
Was that the guy on the diving board?
May have been an example like that. It seems like it was. how did we get to 4.9? That was exactly half of the acceleration due to gravity in the metric system, SI system, which was 9.8 meters per second squared. Half of that was 4.9. Well, if you do the same thing here, this must be half of the acceleration due to gravity on the moon. That would make acceleration due to gravity on the moon 1.62. Okay? And, whoops. Now, I basically almost gave it away. Didn't quite give you the answer, but close to it. Okay? So that's where this one comes from. Now, the term that we used in the general sense also had another, the equation we used in the general sense had another term in here, a t term. Anyone remember what the t term referred to? The coefficient of the t term was v naught, which was the initial velocity. Well, if you drop the hammer and the feather at the same time, what's its initial velocity? Zero. So that's why you have no t term in there, because it was released from rest, which means zero. Now, what do you reckon that 2 comes from? Yes, that's your initial position. And let's say that David Scott was about, maybe he did it like this, either he was a tall dude or he lifted him up like this, 2 meters above the ground. Because 1 meter is about 3 feet, another meter is a little bit more than 6 feet, and I'm right a little over 6 feet, so that would have to be about here. Okay, 2 meters would be about like that. Okay, so that's where the 2 came from. Okay. Now, where S of t is the height in meters, so t equals 0, then this height was 2 meters. Okay, and t is the time in seconds after he released them. What is the ratio of the Earth's gravitational force to that of the moon's? Okay? Now, I know what they want you to do. So, Elijah's here. I kind of think I know what they want you to do. Okay? Yeah, okay. Their verbiage, their nomenclature is off, okay? What they're really asking for is the ratio of Earth's gravitational acceleration to that of the moon. You don't call it a force if you go and say it's 9.8. 9.8 is acceleration due to gravity, not force due to gravity. Acceleration due to gravity. Now, sure, if you had a 1 kilogram object, that would be 9.8 would be its force in newtons. So this really should read acceleration. But this is a math book. They don't get their terms, physics terms right. This would be acceleration. Okay, sorry about that. I'm not going to teach physics. Irritates me. So guess what? We don't have to do any real calculations except that I said I almost gave it away. What do we say the acceleration due to gravity on the moon was? 1.62. So it says what is the ratio of Earth's gravitational acceleration, which would be what? 9.8 meters per second squared. They're leaving out this, to, what did you just say it was on the moon? 1.62 meters per second squared. So the units go out, so the ratio of these accelerations would be, anyone got a calculator there? Pretty close to 6 to 1, isn't it? Say again? 6.04. Okay, 6.04. There's the ratio. About 6 times. The Earth's gravitational acceleration is about 6 times that of the moon's gravitational acceleration. Okay? And actually, technically, you should only use 2 digits anyway, so that would round to 6.2. only had 2 digits coming in there. You had 3. Actually, you only had 2 digits coming in here too. So either way, about 6. And they do 6.0 approximately. Good deal. Okay. And basically they did it the same way I did. I've written things out a little bit longer and more precise or something, but you get the same results. Now, in 2.3 exercises, for those of you who had the same author in Precalculus Algebra and Precalculus Trig, which I'm guessing most of you did, generally here he had fill in the blanks for the concept quick check. Here, basically, it says describe the product rule in your own words, the quotient rule in your own words. What are the derivatives of tangent, cotangent, secant, and cosecant, and higher order derivatives? What is a higher order derivative? Basically, just going back and getting the data from the book. So I'm not going to ask you to repeat all that. You can do it on your own. So, homework exercises. Any of the odds, 5 through 9, all of those are at calcchat.com. 5 is at CalcView. Any of the odds, 11 through 15, all of them are at CalcChat. 11's at CalcView. Any of the odds, 17 to 21, they're all at CalcChat. 21's at CalcView. Any of the odds, 23 through 27, they're all at CalcChat. 23's at CalcView. Any of the odds, 29 to 39, they're all at CalcChat. None of those are at CalcView. Okay? Any of the odds, 41 to 55, they're all at CalcChat. 41's at CalcView. Do number 57. The only odd one like that, you can probably figure that out on your own. It's a CalcChat, though, if you need additional help. Do either 59 or 61. They're both at CalcChat. Neither one are at CalcView. Goodness, I'm having trouble breathing. Any of the odds, 63 to 67. They're all at CalcChat, none at CalcView. Do either 69 or 71. They're all at CalcChat, not at CalcView. But by the way, and this being, of course, one of my top classes, and I've had 4 people turn in papers so far. Very good, but that's still pretty low. Not quite half the class, and we're almost at half the term now, folks. I think this week ends the first mini-term. Second mini-term starts next week sometime. Tuesday, I believe. Okay? So, should be getting some more papers in, wouldn't you think? And by the way, the month of February is coming to a close, so that bonus point, 2 bonus points you get in February, go down to 1 in March. Okay, so please get your papers in sooner rather than later. But why I stopped there at 69 and 71, these graphs are called, and this is a really terrible term for it, the witches of Agnesi, or Agnesi. I don't know how you pronounce her name. But she was one of the very, very early women mathematicians, very famous mathematician. There were a few that preceded her, but not very many. And unfortunately, they called these witches because of a translation error. It was actually called something else, and when they translated it either from Latin or to Latin or from wherever, Italian or whatever her native was, they mispronounced it and called it a witch rather than a chart or a graph or whatever it stood for. So the term witches are sort of crazy, but Agnesi would be a good paper topic, or how she came up with these witches of Agnesi, or what that actually meant to her. But there's at least a couple of different paper topics you could get out of that. So that's why I did a timeout there. Okay, then do any of the, either 73 or 75 or both. Both of them are at calcchat.com, 75's at CalcView. Do number 77. Okay, it's just one little problem there. I think you could do it. Then do 79, just one problem there. Do 81, just one problem there. But then for the rest of these, 81 through 89, do any of those odds. All those odds should be at Calc Chat, none of them are at Calc View. Then, doing second derivatives, and I'm surprised they didn't have you exercise more on second derivatives, but they're pretty easy to do. Any of the odds 91 through 99. They're all at Calc Chat, 91's at Calc View. Then do either 101 or 103 or both. They're both at Calc Chat, they're 101's at Calc View. And then do either 105 or 107. They're both at Calc Chat, neither are at Calc View. And then, exploring some concepts, you can look at 109 if you'd like, think through that, whatever. Do the same for 111, and or the same for 113. All of those should be at Calc Chat, none of them are at Calc View. Okay? And this guy actually also has another website called MathGraphs, okay? So you can use that website as well. And, whoa, let me step back a bit. Yeah, okay. Then do any of the odds, 115 to 119. Okay? They're all at Calc Chat, not at Calc View. Do 121. It's a Calc Chat, not a Calc View. 123 is probably fairly interesting to look at. Okay? 125 also. They're both a Calc Chat, not a Calc View. Then do any of the odds 127 to 1, either 127 or 139. The 129, can't talk. Now that almost looks like that's getting into something beyond really what I consider the scope of this course. So if you find those too complicated, forget it. You'll hit that in differential equations if you continue for that. Any of the odds 131 to 135, hopefully all those are at Calc Chat. They're not at Calc View. And then 137, excuse me, I'm having trouble breathing, is a proof. And if you want to go for it, by all means go for it. All right, any questions? 2.3. All right.
So
yes.
For a second derivative, you just take the first derivative and then take a derivative again?
That's exactly it. That's all. I forgot that example 10 did have this worked out, so let's go on and do it. To find the acceleration, differentiate the position function twice. Because when you differentiate it once, you'll get a velocity function. When you differentiate twice, you get the acceleration. Okay? We thought through it and got it, but let's do it this way. That's what we're doing, it's taking derivatives, right? What is the derivative of s of t? In other words, what's s prime of t? What would that be? Say again?
Oh, the minus 1.62 t?
T, yeah, because 2 has a derivative of 0. Okay, so that would be so s prime of t, which, by the way, is the same as v of t, is equal to negative 1.62 t. Right? Take it again. S double prime of t, which, by the way, is the same as v prime of t, which, by the way, is a of t, okay, would be what? Negative 1.61. There is your acceleration due to gravity on the moon. A constant, negative 1.61. Okay? That's on the moon. Okay, there they did the first one. There they did the second one. Because S double prime is equal to minus g, the acceleration due to gravity on the moon is the 1.62 meters per second. And compare that with the acceleration due to gravity on the Earth. See, this time they're saying it right, accelerations. Okay, and then they turn around and call it force. Okay, their accelerations, okay, due to gravity on the Earth is 9.8 meters per second per second. So the ratio of the Earth's gravitational acceleration to that of the moon's is, so, I'm going to do it every time. Acceleration. Okay, it irritates me. 9.8 to 1.62, which comes out about 6.0. Okay, because you only have two single digits, so rounds is just 2. They did that part right, and that's a ratio. It has no units. All right, and that ends. I've already given you homework exercises. 2.3. Forgot about that. Sorry. Okay. So let's discard that. Any questions on 2.3? Let's move on to 2.4. All right, that was getting so easy, wasn't it? You got to do derivatives, and they turned out being pretty easy. Take second derivatives, third derivatives. They were easy too. They were just derivatives, right? And all this is just way too easy, right? Well, guess what? We can make it a little more, because we're going to continue with differentiation, but this time we're going to get to, we had the sum rule and the difference rule. They were pretty straightforward. The product rule and the quotient rule, a little more involved. Now we get to something called the chain rule. Okay? Now, what in the world do we mean by that? The chain rule is used for finding the derivative of a composite function. Now, do you remember back from pre-calculus algebra what a composite function is? It's a function of a function. Okay? And f of g of x. F circle g of x. Remember that little thing? Yeah. That's what we're dealing with here. And that's the whole reason you did composite functions back then, was so we would be ready for them here in calculus. So we'll find the derivative of a function using the general power rule. I think we've pretty much already done that, but maybe we're going to generalize it a little bit. We'll simplify the derivative of the function using algebra. That's what we've been doing, combining like terms, moving terms, okay? And we'll find the derivative of a trigonometric function using the chain rule, which will be the same here. But that's when you have a trigonometric function of another function, or a function of a trigonometric function, okay? That's when you use the chain rule. So we have yet to discuss one of the most powerful differentiation rules, the chain rule. This rule deals with the composite functions and adds a surprising versatility, oh, that's nice, isn't it, to the rules discussed in the 2 previous sections. In fact, it's how I remember, say, the quotient rule. I just do with the chain rule. It's a lot easier to deal with, I think, than the quotient rule is. Even though the quotient rule is pretty fun, low-D, high, yeah, that kind of mess. So, for example, compare the functions shown below. Those on the left, these, can be differentiated without the chain rule. Yeah, we know how to do this. Derivative of this is 2x. Derivative of this is x. Yeah. Derivative of this is 3. Okay. Derivative of this would be plus. Second?
Oh, it's
secant squared. Yeah. Secant squared. 1 plus secant squared of that. Okay? But is there any way to do this? You have to use the chain rule. There's no way without the chain rule that you can figure out how to do this. This one too. Okay? This one. Okay? Yeah, there is a way. I'd rather not do it, though. You can do this without the chain rule. What you could do is take 3x plus 2 and multiply it by 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 3x plus 2. That'd be 3x plus 2 to the 5th power. Do all those multiplications together and then go back and take the derivative of it. I'd rather not. I'm way too lazy to do that. So thank you, chain rule. You're going to give me a much easier way to do this. And it will be. And this one, now, I want to point something out to you. This is x plus the tangent of x squared. That's not tangent squared x. That one we could do. No, we couldn't either. Okay, but this is, don't confuse that. For this tangent squared, the square would be here. This is tangent of x squared. Can't do that without the chain rule. Basically, the chain rule states that if y changes dy du, basically the chain rule states that if y changes dy du times as fast as u, weird way to put it, and u changes du dx times as fast as x, then y changes as the product of dy du times du dx times as fast as x. That is a weird way to express it in my mind. But it's true. It is absolutely true. Okay? And we're basically, they've almost given you the chain rule here. Not quite, but almost. So here's example 1. A set of gears is constructed as shown here in this figure. 2.24. Oh boy. All right. I'm trying to find the driver here. Okay. As the first axle revolves, so what you're going to do is you're going to take this crank and turn it. Okay? As the first axle revolves, it drives the second axle. So you turn this one, and because this has so many teeth compared to so many teeth there, that's going to drive this one. You're going to have to go several times around to get that to go around once, right? Okay? But when that goes around once, then that turns this around once. Okay? Now that looks fairly close to this one, maybe a little bit smaller. I have to count the teeth to see. And that's going to turn then this one, which then is going to turn axle 3. Okay? Now, let y, u, and x represent the numbers of revolutions per minute of the first, the second, and the third axles, respectively. Then it says find dy du, how fast y changes with respect to u. That's first with respect to second. Du dx, and then finally dy dx. Okay, now, I can tell you right now, dy du is going to be a pretty small number because the rate of change of y with, let's see, is that right? Represent the number of revolutions per minute of the first, second. So, no, actually it's a pretty large number. Dy du, because y's got to go several times for every one turn of u, which is turning of axle 2. Okay? Now, then du dx, that's this with respect to that, it's going to be a pretty large number. Not as large as this one, but still a pretty large number. Okay? And then show that dy dx is the product of dy du times du dx. Okay? All right. Because the circumference of the second gear, and let's go back to this and see. Okay. Here's what they're showing you. That's the radius of gear 1. Here's the radius of gear 2. Okay? And that, if this is 1, that's 3. That's 3 times that. Okay? Now, okay, and here they show. I said they look like they're about the same. I didn't think they quite were. But gear 3 is also 1, so it's the same size as this one. And gear 4 then is twice the radius of this one. Okay? So, okay, sorry, let's go back here again. How is circumference related to radius?
Radius times
Yeah, the radius is this length, and the circumference is that. And you're getting pretty close to it.
It's a radius squared times.
No, don't square it. Circumference is 2 pi r, okay? Or pi d. That's the easy way for me to remember. The circumference is pi times the diameter of the cube, okay? But the diameter is twice the radius, so it's 2 pi r. So circumference is 2 pi r. This circumference is 2 pi r. The r is larger. So because the circumference of the second gear is 3 times that of the first, because its radius is 3 times that, okay? The first axle must make 3 revolutions to turn the second axle once. So that's a 3-to-1 ratio. So its derivative of y with respect to u, y being the number of revolutions per minute in the first one, to u, which is revolutions per minute in the second one, that's going to be 3-to-1. Okay, so or 3. Similarly, because the second axle must make 2 revolutions to turn the third axle once, okay? So the second axle, called the second derivative, du dx, has to be 2, okay? And then, so y turns 3 times to turn u once, u turns twice to turn x once, okay? Then dy dx, that would have to turn 6 times to turn x once, okay? That's what they want you to see here. I jumped a little bit ahead. Combining these two results, you know that the first axle must make 6 revolutions in order to turn the third axle just 1 time, okay? There's a little bitty gears there, and it takes a lot of turns of that first one to make the third axle turn. 6 of those. So you can write dy dx is the rate at which the first axle changes with respect to the second times the rate of the second with respect to the third. Okay? Now, written in other ways, dy du times du dx. Okay. Now, pure mathematicians would cringe for me to say this, okay? But what does it look like is happening here? If the du's are canceling out, you get dy dx equal dy dx. That's not what's happening, so don't think of it that way. But it sure makes it easier to remember, doesn't it? Okay? But that's not. These are derivatives. They aren't things you cancel out. But it sure does imply that, doesn't it? So, don't think of a big black horse, okay? Whatever you do, don't think of a big black horse, right? Okay. You're not going to do it, are you? Okay. All right. So it's 3 times 2, which is 6. Okay, they put that in there for us, okay. And sure enough, that's what's happening. The rates of change of the first axle with respect to the third is the product of the rate with the first with respect to the second times the second with respect to the third. In other words, the rate of change of y with respect to x is the product of the rate of change with y with respect to u times the rate of change of u with respect to x. They've just done it several ways now. Okay. So here is theorem 2.10. Okay? The chain rule. if y is some function of some variable u, and it is a differentiable function of u, but u is also some function of x, g of x, and that's also a differential function, this time of x, then y, which is the function of f of u, but u is g of x, that's your good old composite function definition, f composed with g. Okay? Then that y as a function of g as a function of x is also a differential function of x, and that dy dx, the derivative of this with respect to the innermost variable there, is dy du times du dx, just like we did. Or, here's another way to express it. To me, this might be a little more straightforward. D by dx of f of g of x would be f prime of g times g prime of x. Okay? This is f prime of g here. Okay? U was g of x, right? Times du, which is g prime here. Du dx is g prime. Now, this to me is kind of the best way to approach the chain rule. Now, look at what it says. Take the derivative of this function with respect to the innermost function there. First, take the derivative of the outer function with respect to the inner function. Then take the derivative of the inner function. Okay? And that's what you do with the chain rule. Now, after a while, the order doesn't matter. You can take that derivative of the innermost function first, and then take the derivative of the outer function with respect to the inner function. You can do it in any order you want to. But I always learned it, take the derivative of outer with respect to inner, then take the derivative of the inner. Okay. When applying the chain rule, it's helpful to think of the composite function, f composed of g, as having two parts, inner part and outer part, exactly what I was saying. Okay, y is f of g of x. That's the outer function of the inner function. The inner function g of x is equal to u is equal to g of x. The derivative of y is equal to f of u is the derivative of the outer function at the value u of the inner function times the derivative of the outer function, inner function, which is u prime or g prime. So this is true, but I feel like it's a little sloppy. Because if I see a prime here, and a prime here, of course I'm thinking these are all with respect to the same thing. They're not. U, of course, is with respect to x. Okay? Y then with respect to x. But f is with respect to u. So I don't really like using the primes here. I think it's better to use the d by dx. You know, that makes it a little bit clearer. Okay? But really, in real life, when you don't have all these other things messing it up, it's pretty easy to pick out. So here's example 2. Let's do this. Okay? Now, all right. Let's start with the innermost. U is x plus 1. Okay? That's your g function here. Okay? Is g of x is x plus 1. Now, y over here is your reciprocal function of g, f of g of x, which is your u plus 1. And that would then make the corresponding here, y is equal to 1 over u, because this is 1 over x plus 1, u is 1 over that. So there is your outer function there. Why even mess with the u? It just sort of confuses the issue, but that's really how you're doing this, okay? Now, if you had been given the problem like this, how would you do it, based on what we know already?
The
quotient rule, of course. Okay? But just like we did before, I think you might remember, you could write, ooh, let me get my pen back. You could write this as y is equal to x plus 1 to the minus 1, isn't it? Okay? That way, if they gave you this problem, I do that by the quotient rule. If they said find the derivative, let's just do it, okay? But, because I really don't like the quotient rule, I would turn around and write it like this, and now let's do that. What is your, what would be your y prime here? And there I'm putting the prime in here, even though, what would you do here?
Negative x.
Or negative 1, right?
Oh, yeah.
Okay, negative 1, x plus 1 to the negative 2. And then the chain rule says derivative of the inner function. Well, what is the derivative of the inner function? Derivative of this, du by dx. 1. Okay, so it really has nothing to contribute there. So this would then be minus 1 over x plus 1 squared. Okay. Here, it wasn't necessary to use the chain rule at all because du dx, derivative of the inner function, was 1. Okay. So this is a little oversimple problem, but that's how I would do it. Let's think about the quotient rule. Okay. Quotient rule would have read what? Y prime would be
X plus 1.
yeah, low, x plus 1
Times 0.
times 0. Okay, that goes away, doesn't it? Minus
1
yeah,
times 1.
no, yeah, 1 times 1. I'll put it that way, okay, since you're doing it, yep.
And then over x plus 1 squared.
Which would be, this is 0 minus 1 over x plus 1 squared. Same thing we got before. I really like this way better than quotient rule. Not that I dislike quotient, I do. I mean, I really don't care for quotient. It has a cute little thing, low d high minus high d low, overload low. That's cute, but if I can avoid it most of the time, I'll do something like that. Okay? This is the chain rule, that's the quotient. I think this is a lot easier. Okay? Especially if your du is 1. That's really easy. Okay. Let me clear my scratch out of the way. And let's see what they're going to do next. Oh, here's another one. Okay? What will your y prime be here? Remember what the chain rule says? What's that? Is y prime what?
The inner or the outer?
Yes. Okay, it's both. Okay, you do them both. You first take the derivative of the outer function. What's the derivative of the sine? Cosine of the inner function, which is 2x. But then you take derivative of the inner function, which is 2. So this would be 2 times the cosine of 2x. That's it. You take the derivative of the outer function being sine, that would be sine of the inner function, cosine of 2x. And then the derivative of the inner function is 2. I like to bring that out front because then you might think this is cosine of 4x. It's not. That 2 is multiplied. That's not. Okay? And see, that's the derivative would be derivative of sine of u times du dx. And that would be. So, it looks like they're going to do the problems, giving one at a time, then they'll come back and do them all. So let's do this one. Whoa! What in the world are we going to do with that one? What would be your... Let's first rewrite y. I think I told you before how I like to rewrite these. How's that? Just like I don't like to write...
Want to get rid of the root.
Get rid of the radical. How do we do that? Second? 3x squared minus x plus 1. What's inside the radical? Your g to the 1/2 power. Okay. Now in that form, let's go for it. Y prime would be what? Outer function first. 1/2 3x squared minus x plus 1. Do the whole inner function there to the negative 1/2 power, and then multiply that by the derivative of the inner, which would be 6x minus 1. Perfect. Okay, now if you want to write that a little differently, you can put this now, remember, as a numerator. That is your numerator. 6x minus 1 over 2 times the square root, if you want to put it back in radical form, 3x squared minus x plus 1. There's your answer. Could have left that in exponent and make that to 1/2 power. But since the original problem had a radical in it, keep the radical in it. Doesn't matter. Doesn't matter to me. To WebAssign, it matters. I don't know which one they're looking for, and I couldn't tell you which one they're looking for. I'd have to guess, and if they said this one's wrong, I knew it was right. I tried a different one until I figured out which one they really wanted. You know, this is, either of those are perfectly good answers. Yeah, I tend to want to put the minus exponent down here, so yeah. Either way. Any questions on that? Now, they haven't gotten around to doing it, but you are getting it down, right? And we'll go back and check when they do them. Okay? So let's see. D. Y is equal to tangent squared x. What's your innards and the outwards there? The outer is the squaring function. The inner is the tangent function. Okay? So our y prime would then be how do you do a squaring function first? 2 times the tangent to the first power of x. Right? That's the derivative of the outer function, the squaring function. Then what you have to multiply it by derivative of the tangent. And what is the derivative of the tangent? Secant squared x. So here's our answer to tangent x secant squared x. That's it. That's done. There is your chain rule for that. So do the derivative of the outer function times the derivative of the inner function. Identify the outer function as the squaring function, inner function is the tangent function. Okay? All right. Let's see, is there one more? They have room for it. Let's see if there is. No. Whoa. Look at that. Oh, I'm sorry. All they wanted you to do was decompose those. We actually took the derivatives up. Sorry. All they were looking for was inner function, outer function. inner function x plus 1, the outer function 1 over u. Outer function sine, inner function 2x. That's all they're looking for. Outer function, the square root function, inner function, the thing inside here. That's all they were asking you to do. We went on and did the next logical step. Outer function, the square root function, inner function. What's that? Yes, we went on and did what we were supposed to. Now, let's go to, they're skipping example 3, so let's go back up and do example 3 here. Find dy dx for this function. Let's see, example 3. Y is equal to x squared plus 1 squared. No, cubed. I can't read. Okay. Find dy dx. What would that be? Okay. Good start. 3 x squared plus 1 to the second power times 2x. Very good. Now, that to me is a perfectly, well, it's not maybe the best one. I would multiply these two together and get 6x times x squared plus 1 squared. To me, that's a perfectly simple answer for that. Okay. Now, I know y'all are wanting to do this. I know from the bottom of my heart, when you first looked at this, I want to expand that that binomial. Yes, you did. I could tell it in your ears, you know. If you remember how that works, this would be good old Pascal triangle, the first term cubed, which would be x to the 6th. Remember that? Times 3, plus 3 times x, x to the 4th plus 3. Plus 1 to the first power, okay? Then you had another 3 times x, 3x squared plus 3. And then you had plus 1, okay? Because it was the first term, okay, you start with the first term to the third power, that would be this one, plus 3 times the first term squared, times this to the first power, 1 to any power is 1, plus 3 times this thing squared, plus this, so to the second power, which is still 1, plus this to the 0th power, and this thing to the third power, which is still 1. Okay. So let's see what we got there. That would be x to the 6th plus 3x to the 4th plus 3x squared plus 7, right? I think that's it. Okay. Now let's do our y prime. dy dx would be what? Not that hard. 6x to the 5th plus 12x cubed
plus 6x
squared. Right? Now,
is the last one squared?
what's that?
Shouldn't it just be 6x?
You're right. I'm sorry, 6x. Got carried away there. Yep, 6x. Okay, now, first thing I notice there, each one of those terms has a 6x in it, right? So let's factor out a 6x. And what do you have left? X to the fourth.
Plus 2x
Squared. Plus 1. Right? And do you happen to notice that that's a perfect square trinomial? 6x times x squared plus 1 squared. Which is exactly what we got back there. Ho-de-ho. Okay? Now, which you reckon is easier? Chain rule routes or multiplying that out and taking the root of this right there? Love that chain rule, okay? Go for it. Okay? Okay. And they get 6x times x squared plus 1 to the second power. All right. All right, next is the general power rule. Yeah, it's not hard to show it. Well, let's see, maybe it's going to be harder. The function y is equal to u of x to the nth power is one of the most common types of composite functions. What do you reckon the inner function is? U of x is what's inside the innermost thing of the function. The outer function is the power functions. Y to, or let's call it z to the n. U to the n. Well, yeah, u to the n. That's exactly what it is. U to the n. Okay? So the rule for differentiating such functions is called the general power rule. Special case of the chain rule. What do you reckon it would be? What do you reckon your y prime here would be? You tell me. Y prime would be
u of x.
how about start with that? N times u of x to the, let me put this in like this, to what function, to what power? N minus 1 times u prime of x. Right? Times the derivative of the inner function. That's it. The rule for differentiating such functions is called the general power rule. Special case of the chain rule. Just do it. N times the inner function to the n minus 1 times the derivative of the inner function. Chain rule. And let's see how they phrase it. If y of x is equal to that, u of x to the n, where u is a differentiable function of x, got to be, n is a rational number. Doesn't have to be an integer. A rational number. It could be the negative 5/8. You can still do it. Okay? dy dx then would be dy dx, the outer, with respect to the inner, would be dy dx would be n u to the of u of x to the n minus 1 times du dx. U prime, whatever. Or equivalently, d by dx of u to the n, that's saying the same thing, is n, where is there? N of u n minus 1 times u prime. That's more like what we said. Okay. All right, now, in your text, they do a little proof on it. So by all means, look at that, especially if you're a math major. You may find it interesting. We will start next time at example 4. Okay? Any questions? Let me give you a few homework exercises in this section, 2.4. I think you can do any of the odds 3 through 7. They're all at Calc Chat, 3's at Calc View. I think you can do any of the odds 9 through... Try as many of that 9 through 33 as you'd like. And we will, if some of them get a little complicated for you, hold off. We'll do a few examples and come back and do the rest of those. They're all at Calc Chat. Only number 9's at Calc View. So I know you can do 9. Pretty sure you can do 11. But if those get a little hairy, hang up on them. We'll do them. Okay. Good deal. Any questions? Good class. Good folks. Glad I didn't have to leave and clear my head. Worked out okay.